All right, hey everyone. Thanks for bearing with us there. I'm Ian,
I'm Pablo. Hi.
and believe it or not, we do actually make sound when we move our lips, so hopefully that'll work out fine this time. So let me just tell you a little bit about what CodeJam is. It's a contest where we write tough algorithmic problems, and then you write solutions to them. And one neat thing about CodeJam is you can write these solutions in just about any language you want. A lot of contestants use things like C++ and Python, but we also get submissions in like LOL code and whitespace and even Shakespeare, so lots of variety. So CodeJam is actually 14 years old. It's even older than Android, believe it or not. And it's really important to Google, not just as a way to attract new talent, but also as a way to just share the joy of thinking about these tough algorithmic questions. And I keep saying tough, but rest assured you can dive right into CodeJam. There's a whole bunch of different rounds of increasing difficulty. And when I first started competing in 2011, I'd only just learned to program. I had never done a programming contest, and I was still able to have a great time. So a few stats about CodeJam. Every year we have tens of thousands of participants. We hope that if you haven't done it before, you'll help us increase those numbers. It's a worldwide contest. Most of it is online, and then the final round is actually like on site in a different world location every time. We've done Dublin before, London, New York, Tokyo. This year we're returning to Dublin, and we're excited about that. And then as of 2015, we have a parallel track called Distributed CodeJam, where you write code that runs on 100 different nodes at a time, and like those nodes are communicating with each other, and you can break up a problem and solve something that you couldn't solve in a non-distributed way. So that's all fun. And let me also say a little bit about 20% time at Google. So we have this notion that 80% of the time you can work on your primary project, and 20% of the time you can do something completely different. So we have lots of people at Google who work on all kinds of different things who also help with CodeJam. They submit problem ideas, they help us review problems, they help us prepare them, and that kind of keeps the contest more diverse than it would be if just the full-timers were writing it. So I'm going to talk about one of my favorite problems from last year. It was written by Pablo, who you'll hear more from in a second, and it's called Slides with the exclamation point. And it's about using giant slides to slide between buildings. And we don't have this technology yet at Google, but who knows, maybe someday. So the problem is about a thinly disguised version of Google called Ghoulie that has a total of B different buildings. Here there are 6 of them in this illustration. And the CEO of Ghoulie likes to get to her favorite cafe, and walking there would be boring, so she's going to get there by giant slides that connect the buildings and go one way. So there's lots of ways we could build slides between buildings. This is one of them, for instance. And what makes this problem a little more difficult is, so like when I was a kid and my mom was driving me home from school, I'd be like, oh, let's go a different way, let's go a different way. Like I like variety, and so does the CEO. The CEO wants to have a particular number of ways to get from her office to her favorite cafe. So for instance, here there are 3 paths. There's the red arrow is connecting like the top 3 buildings. The yellow is like goes through the top 2 and down and so on. So there are 3 different ways for her to get to the cafe there. So in this problem, what we do is we give you 2 pieces of data. We give you the number of buildings and the number of paths that the CEO wants. You have to have exactly that many paths. And there are 2 different levels at which you can solve this problem, like in many CodeJam problems. Either there's only 6 buildings and the number of paths is only up to 20, or there could be 50 buildings and up to 10 to the 18th different paths. So the large one is quite a bit harder than the small. To talk us through this problem, I'm going to hand it over to Pablo.
Okay. Thanks, Ian. So now that you had some time to think about it, and if you actually compete, you'll have a little bit more. We'll talk about the solution and like the thought process that someone will need to go through to actually get it. So we start with our drawings of buildings and slides, and the key thing we need to notice to solve this problem is that we can't really have paths that go from the office to the cafe that go through a cycle. Like in this illustration, you can see that we've added a slide that makes a cycle marked with a yellow arrow, and there's the path above. And the problem with this is that if you have that, then you'll have like one path that goes directly from the office to the cafe, another path that goes from the office goes 1 through the cycle and goes to the cafe, another path that goes from the office goes twice through the cycle and to the cafe, and so on and so forth. So you will end up with infinitely many paths. And since the input asks for a particular integer number m of paths, infinity will never be equal and will always be greater to that number. So as long as we have that cycle, we are never going to comply to what the input is asking. So after we made this key observation in the problem, and we know there will be no cycles that can go through a path, we know that there's something called a topological sort of the buildings, which means that we can put the buildings in order such that every slide goes forward, as you can see in the example in the picture. So basically, if we number the buildings from left to right, every slide goes from a lower number building to a larger number building. And this is really neat because half the possible slides are gone once we establish this direction. And this is more or less enough to solve the small by brute forcing the possibilities. Given that we only have 6 buildings, this fixed direction leaves us with only 15 possible slides. We have 5 possible slides that start at the office, only 4 that start at the second building from the left, and so on and so forth. And that accounts for 15 possible slides in total. And that means there's only 2 to the 15 combinations of slides, right? Because each of those slides could be present or not be present. So we can, because 2 to the 15 is not a large number for a computer, it's less than 50,000, we can try all of those. For each of those, we need to count how many paths it will resolve from the office to the cafe. And again, since there's so few buildings and every path has to include both the office and the cafe, the only thing we need to check here is which ones of the other buildings will be including, since again, we know in which order they will be transversed. So again, there's up to 2 to the 4, because it's 6 minus the 2 that are forced to be in the path. And then for each of those combinations of buildings, we can check whether that's a path or not, depending on which slides we've included. And then just for all those possibilities of slides that we are checking, if any of those has exactly one path, then we just output that combination. And then we have solved a small version of the problem. Now, there's several ways, of course, to think about problems, but one thing I would like to introduce here is that you can use data, especially once you have the small solution or any solution of a smaller version, to try to inspire you or actually hint you into what to do next. So in this case, since we solved the small, we can check what happens for all combinations of B and M that comply with the small limits. In this case, we have each row represents a different value of B, and each column represents a different value for M. And we have painted in green the combinations that result in a possible solution. That means there's some combination of slides that achieve that combination of values, and red is when there's none. And we can immediately see 2 things here. The first thing that's important to notice is that all of the values that are possible are together, and all of the values that are impossible are also together. So it seems like everything is possible up to some value of M, and then when that value gets too big for the number of buildings, then it's impossible. And the other thing that we can notice is that there's a particular well-known shape for how this maximum number increases. The maximum is 1 for 2 buildings, 2 for 3 buildings, 4, and then 8, and then 16, which is a simple exponential with base 2. And this makes sense, right? Because if we think that the maximum for a maximum possible M is 2 to the B minus 2 for any given B, that makes sense because the maximum will be accomplished whenever we use all the possible slides. The more slides we put, the more paths that are possible. It will never, including a slide, will never decrease the number of possible paths. And if we include all slides, it's not hard to prove that there will be 2 to B minus 2 paths. Of course, when I say all possible slides, I'm only referring to the slides that go in the appropriate direction, according to the key observation we talked about in the beginning. So then, we can use the fact that this is that the powers of 2 combine nicely to fully solve the problem. So if we put all possible slides between every node except the office, and then we add a slide from building 1, which is the office, to building B, which is the cafe, that will include only one path. But then, since we put all the other slides, starting at building B minus 1, there will be a single path to the cafe. If we start at building B minus 2, there will be 2 paths. If we start at building B minus 3, there will be 4 paths, and so on and so forth, every time multiplying by 2. So we can just use the slides that start at the first building, the office, to write the M minus 1 paths that we are missing in binary, and just pick and choose which powers of 2 we want to include. And if we do that, we can construct any graph with any number of paths between 1 and 2 to the B minus 2, and we've already shown that there can be more, so that gives a full solution. If if m is larger than 2 to the b minus 2, then we output impossible, and otherwise we use this procedure to build the output graph. To see this more visually in an example, here we have b equal 4 buildings, and we know that m larger than greater than 4 is impossible because 2 to the 4 minus 2 is 4. And then here are the 4 possible answers for the possible cases. In case m equals 1, then we already have the one path going directly from the office to the cafe, illustrated here by buildings 1 to 4. And if m equals 2, then that's 0, 1 in binary, so we only need to include one slide from building 1 to building 3. If m equals 3, that's 1, 0 in binary, so we only include one slide from 1 to 2. And if m equals 4, then m minus 1 in binary is 1, 1, and then we have to include both slides. And we won't do that now because it will take too much time, but you can check in all these drawings that the number of paths that are possible between building 1 and 4 is always the required one. So that concludes the account of the solution. Before diving into questions, I would like to invite you to join us on our social channels in Google+, Twitter, and Facebook, and also visit our website at g.co/CodeJam, where you can already register for the 2017 season of CodeJam. So now we'll go read some questions that we received during this stream.
We go back on camera. Hey everyone. So one question we get a lot is like how to prepare for CodeJam and for other similar contests. There's no real substitute for just trying a bunch of previous problems. There's a list of past problems on our past contest page that lists some particularly accessible ones. You kind of want to start off with some easier ones and then work your way up. I would recommend like working on a problem for maybe an hour, and then if you can't see what to do, you can maybe look at our analysis where we explain how you would approach such a problem, or look at some past competitors' code, which you can download and see how they approached it. Do you have anything else to add on that?
Yes. So, of course, there's some topics that you can study that will help, like knowing math or knowing algorithms or a bunch of different computer science topics will help you with the contest. But yeah, there's no substitute for practice. And also, if you start by practicing, it will motivate you to study what you really need instead of just studying some random topic and then hoping it will help. And also, I would like to ask that practicing this type of contests is not only useful to do well at them, but also to be a better programmer, a better scientist, and possibly get a job eventually.
And then we also get asked a fair bit about the qualification round, the first round of the contest, and it works a little differently from the others, so let me just say a bit about that. It runs for 27 hours, but don't worry, you're not going to be like coding for 27 hours straight. Like sometimes that happens at work, who knows, but like you only need to get a certain number of points to advance in the qualification round, and you'll know exactly how many points that is. So you can just keep solving problems until you hit that total. And you can keep going if you want. We always put in some problems in the qual round that are pretty tricky and might not work as well under time pressure in other rounds, but are fun to think about for a while. So if you can solve all the problems in the qual round, then like you're in really good shape for the contest, but you don't need to solve all of them.
Yeah, we give you 27 hours such that you can choose when to start, especially since this is a global contest that spans all time zones in the world, and you're free that you don't need to feel pressure to start at the very beginning of the qualification round if that happens to be a really bad time for you in your time zone or for whatever reason. Especially because the penalty, so the time it takes for you to solve problems, doesn't matter in the qualification round. The only thing that matters is achieving some specific number of points, and it doesn't matter if you solve all the problems in the last hour, in the first hour, or sometime in the middle.
And then it looks like we have another question about like what are some good resources for learning algorithms and data stuff like this. Gosh, like how much time do you have is kind of the question. There's some great like well-known books like Introduction to Algorithms, the one that people probably abbreviate as CLRS. Donald Knuth has written like a whole library of different algorithm techniques. But I would say like for coding contest purposes, you can look around at different contests and like we've written explanations for all our problems. Other sites have written tutorials on common things that show up. Pablo has a lot of experience with this too, so what do you think?
Yeah, so I agree that there's like a million resources and there's more than any one person can ever read or try. And as I said, I think the best advice is to just practice and try to go find whatever you need. For instance, if you practice with quotient problems and then There's some problem that you can solve it, but you read the analysis, and maybe in the analysis there's some technical terms or algorithms or mathematical theorems or something that you don't know, and then you can go look it up, and that will help you build some body of knowledge that will be helpful in the future without having to first go get a pile of books. Yeah, Introduction to Algorithms is usually like the go-to book for beginners in programming contests. But there's also all kinds of resources, and right now there's a lot of programming contests going, so you can practice with all of them and whichever format you find best. Yeah.
So we have another question. B. Williams is saying some of these problems are rather hard. I don't think you'll see these in interviews. Like, how does this help with interviews or prep for SWE rules? That's a great question. I would say that the problems that appear in like round 1 of Code Jam are often at the same level as interview questions you might be asked, and some of the same techniques tend to show up. So Code Jam can be really good practice for interviews. It certainly like helped me out when I was personally preparing to interview. And like just kind of by nature, there's overlap between the sorts of questions that get asked in on-site interviews and the sorts of questions that come up in Code Jam. So certainly you can't. It's not a waste of time to do this or any other programming contest if you're working on interviews.
Yeah, well, the Code Jam and programming contests in general will definitely help you, because even if the questions are harder, the techniques and the things you practice and the coding and debugging that you have to go through will help you even program things that won't appear in a programming contest. Like most of the development shops out there, you will usually not directly use the algorithms or the data structures or the mathematical theorems, but still like learning to combine them and to debug your code and to write code, bug-free code is great help for job interviews and for work later and all the stuff. And so yeah, the practice is good. If you're practicing for interviews at Google or elsewhere, remember that it's not just about programming or calculating complexity. There might be other topics that the interviewers might be interested in. So don't restrict yourself to just one particular topic.
And also, when you're coding in an interview, like make sure that your code style is good. In Code Jam, when you're just like writing some code like to solve something locally, you might like fall into bad habits of like not giving clear variable names or like having kind of opaque, hard to understand stuff as long as it works fast enough. But when you're showing your code to another human, like in an interview, make sure that you keep that in mind. So we have a question for Pablo in particular saying, how do you practice problem solving? So how do you?
How do I? I haven't practiced directly in a while because I didn't compete for several years, but I competed a lot when I was studying and a little bit after. At that time, so I read a couple of books, and I also I did the computer science in my undergrad, so I had a lot of classes, and when I had electives, I always picked the ones that, or mostly picked the ones that were related. And I also used to train for Math Olympiad in high school and stuff. And I will say, like, again, the thing that I think got me from one level to the highest level I achieved, which is not the highest in the world, but it's decent for me, is practice a lot. Just like register for all contests that are out there and do them. And when you don't have the time because it's at the time that you have to be at work or at class or sleeping, just do them afterwards, but do them seriously as if you were really competing. Try not to go read the analysis or ask for the solution until you really try your best. And when you do ask for the solution, go and implement it, even though if you already have the idea, because implementing is usually the thing that stops us from doing really good.
Oh yeah, I've had plenty of cases where I'm like, oh yeah, I know how to solve this, and then you actually like sit down to try to do it, and like an hour and a half later, it's not working. So yeah, make sure you actually turn your ideas into code. So we have another question here about how many people participate in each round, which I'll field real quick. In the qual round, we have about 60,000 registrants, but then the number of people advancing to like the round ones is usually, I think, on the order of 20 or 30,000. And then after that point, it's actually kind of predetermined how many people advance. The top 1,000 from each of the round ones will go through, so that's 3,000 that make it to round 2. And then it narrows down to 500 for round 3. And by the time of the World Finals, it's only 26 people, including our previous year's champion. So all of those people actually at the World Finals have their own like desk set up, and that's live and in person and on camera and so on. And then let me say a little about distributed Code Jam. If you make it to round 2 of Code Jam, you automatically qualify for distributed, or that's the only way to get in fact. And then that has its own track that leads to its own World Finals.
Yeah, the numbers for distributed are the same as Ian just mentioned. So 3,000 go through the first online round, and 500 go through the second online round of distributed, and then 16 will make it to the, or 21 this year. We'll up it to 21, I think, this year for the finals. So that's two ways you can make it to Dublin and join us for the finals.
So we have, how are the solutions that we come up with submitted? Do they need to be in a specific format? Someone solving the problem using like JavaScript or Excel. So you can solve in any language allowed by the rules, which is virtually everything. You can, I won't quote the terms and conditions like on air or anything, but just about anything, you'll run it locally, and you can submit your source code. The general principle is that like some other hypothetical competitor needs to be able to run your code after the contest and get the same answers that you did. That's what we're really looking for. Otherwise, like style choices, etc., are all up to you.
But to summarize, you will run the code in your own computer and get the correct output. You will download the input from our site, run the code in your own computer that calculates the output, and then upload the output. So we don't really need to run your code. You still need to upload it so we can check that you didn't cheat. But other than that, the code will be run in your own computer, so you know how much you can run in 4 minutes or 8 minutes.
So, speaking of cheating, we actually had a question about that. So let's tackle that real quick. Basically, a very small minority of people cheat in these contests. This is a general problem for like academic computer science too. It doesn't just happen in CodeGem. And we don't want to tip our hand by saying exactly how we do cheating detection, but we do it. We take this seriously. The integrity of the contest is at stake. And we've even had, like last year, we had 2 interns who were working on improving our cheating detection, for instance. So it's something we take seriously.
Yeah, and if you cheat, you will be disqualified from participation. So don't do it. Just remember that cheating is not fun.
And we have, how do you get a CodeGem shirt? Yes, so we're like modeling these for you right now. Just as a quick fun fact, I don't know if you can see it, but on the back of every shirt, it's different every year. Like I'm wearing the one for Seattle, it looks like today. Depends on where the World Finals is. And those pictures are actually made of code that contestants have submitted from the contest. So it's kind of a neat design to wear around.
So to answer the question, to get the shirt, you need to make it to round 2 of CodeGem, so be in the top 3,000, right?
No, you need to be in the top 1,000.
Oh, sorry, 1,000. So you have
I know
to be.
I know this from bitter, painful personal experience when I was like 1,046th or something in 2011.
So you have to do kind of well in round 2 to get the shirt, and that's the first prize you can aspire to. And I think we'll have to be rounding up now because we are running out of time. Please keep asking questions in our social channels, and this will be on YouTube if you want to review it or remember what we said. And remember to register. Go to sheet.co/CodeGem and register for the 2017 contest that will start on April 7th. So you have plenty of time, but just go do it so we can send you an email and remind you and you don't miss it.
All right, yeah, give it a try. If I can do it, so can you.